Hello, I'm Lucas Santos, and today I'm going to present the paper on the design and implementation of real-time resource access protocols, written by me, Giovanni Gracioli, Thomas Cloda, and Marco Cacamo. When talking about real-time systems and its applications, one of the most important things is to get rid of any source of unpredictability, since they are a huge problem to the task's deadlines in real-time systems. One source of unpredictability is shared resource access. Let's see why. On the figure, we have three tasks, numbered from the highest to the lowest priority. The lowest priority task, tau3, executes and accesses a critical section. After that, tau1 arrives and preempts tau3. When tau1 tries to get access to the critical section, it's blocked, and tau3 gets back to execution. The problem is, any task that has priority higher than tau3 and will not execute on the same critical section will get to execute normally, delaying tau1 execution for an unpredictable amount of time. When these medium priority tasks delays tau1 execution, this is called unbounded priority inversion. The way to treat this problem is using resource access protocols that works to bound this priority inversion phenomenon. Our proposal is to build an object-oriented design for resource access protocols for both single and multi-core systems. Our design has to provide low runtime overhead and reusable code. After that, we will implement the proposed design on a chosen RTOS and evaluate its runtime overhead, schedulability ratio, and memory footprint to see if our design is reliable. We designed, implemented, and evaluated the listed single-core protocols: PIP, TCP, IPCP, and SRP. We also implemented the listed multi-core protocols, MPCP and MSRP. This list of protocols gives us many comparisons. We can compare the ceilings protocols against each other. We can compare the single core against the multi-core protocols, and we can also compare the protocols that use fixed against dynamic scheduling algorithms. So first, the design. This is our UML class diagram. We have the synchronizer base class that implements atomic operations like bus blocking. We have the synchronizer common class. It has a chip parameter to choose between FCFS queue and a ranked by priority queue. This is used to store the tasks that are blocked in the semaphore. The semaphore class implements the class key semaphore. Semaphore RT implements some real-time operations that's used by all the semaphores implementations that we did. It has some operations like setting the owner of the semaphore and getting its priority to store it. The semaphore PIP protocol is implemented by the semaphore PIP class. We also have this semaphore ceiling class, which implements methods to set and get the ceiling. So the PCP, IPCP, and SRP inherits from the semaphore ceiling because often uses the ceiling. Even SRP, there is a dynamic. It also uses a ceiling. It has a system ceiling, so we make it inherit from the semaphore ceiling. And lastly, the multi-core protocols. The semaphore MPCP inherits from IPCP because when MPCP is guarding a local critical section, it should behave equal to the IPCP. What is a local critical section? When a critical section, a resource, is only accessed by tasks from the same core, we call it a local critical section. When a resource can be accessed from tasks from any core, we call it a global critical section. So this T parameter here also chooses between a global or local critical section to be guarded by MPCP. If we pass false, this works exactly equal IPCP. And we have also the semaphore MSRP. It inherits from semaphore SRP because it uses kind of the same principle. And he's also responsible for all these T parameters here because semaphore MSRP has a peculiarity because it has to use a FCFS QE to rank the tasks. So we pass this T parameter here, we pass false, so we keep passing false all the way into here, so the synchronizer common class chooses to use FCFS QE instead of a ranked by priority QE. All the other protocols uses a ranked by priority QE. So here we have some examples of how to use our implemented design in C++. The example shows the both multi-core protocols that we implemented. Both pass through here. It means that we are guarding global resource with these semaphores. If you are going to guard a local resource, so you could pass false here. And semaphore MPCP receives two parameters, the value, which is the standard parameter for the semaphore, and the ceiling that works for the local resources. It's a local ceiling for the MPCP. If you are guarding a global resource, you can hide this parameter, you don't need to pass it. The MSRP semaphore is a bit different. It works under dynamic scheduling, so we have to pass a task container, so it can have reference to keep updating its system ceiling. We also have to pass the task amount, and we pass the levels container, which is a fixed parameter, it's a static, so we can choose between which task is going to enter the critical section first. This level is actually what's compared to the system ceiling, and the value with the traditional parameter. So, focusing on our contribution, we want to evaluate the memory footprint, the runtime overhead, and the scalability ratio. This is the evaluation setup that we choose that provides us ways of doing it. We choose that Apple's has the operating system because it's a real-time operating system with low runtime overhead, and also it's written in C, which will help us to achieve that. And we use GCC and object dump especially to measure the memory footprint. So this is the memory footprint in bytes for our implementation. In the left, you can see the class that we implemented. The memory footprint was split in 3 sections. The code, which is the size of the code sections for the functions like P and V operations. The data that has the attributes for the classes, and static data, which has the static attributes. The total memory consumption column, you can see the sum of, for each protocol, you can see the sum of code data and static data plus the class it has inherited from. Here you can see the lines of code on which we can see that it has kind of a relation with the total memory consumption. With more lines of code, you have more memory consumption. For the runtime overhead, this is the application parameters that we used. We used tasks with periods of 50 milliseconds, computation time of 1 millisecond, and we did 100 iterations to take the average of the runtime overhead. In the tests, we varied the number of tasks. For the single core, we did it from 1 to 20 tasks, and on multi-core, we did it from 1 to 8 tasks. Each task in multi-core, each task was in a different core. And we varied the scheduling algorithms. The protocols that used fixed scheduling algorithms used RM, and the dynamic used EDF. And we used the partitioned versions for each algorithm in the multi-core protocols. Here we can see the runtime overhead. In the x-axis, we have the number of threads. In the y-axis, we have the runtime overhead in nanoseconds. Inside the measurement of each overhead operation, we have the correspondent P or V operation overhead, and we have the sleep operation for the P operation, and we have the wake up operation for the V operation, also accounted in, and we have the time of context switch for the OS also measured, and inside of each of these overhead measures. In this section, we can see that the ceiling protocols has pretty much the same value in average, and we can also see the MPCP has the same value than IPCP when working on local critical sections. We can also see the SRPP has higher overhead than the ceilings protocols. Here on this section, we can see the MSRPP has the same value than the other protocols V operations, except for the SRPV, which has even higher overhead. And here you can see the V operations for the multi-core protocols. We can see the MPCPV has the same value than IPCPV again when working on local critical sections. With this graph, you can see on average that the multi-core protocols have higher overhead than the single core, and we can also see that the dynamic protocols have higher overhead normally than the single core protocols. After we measured the overhead, we want to use these values to see if there is any changes from the scalability ratio for the system. This is the parameters that we varied among the scalability evaluation. We use the heterogeneous periods. We varied the critical section size from short, medium, and long. We also varied the utilization from mean values for the light, medium, and heavy utilization. We also varied the number of resources that the tasks can access, and the probability accuracy, which is the task probability of being assigned to each resource. Varying these parameters, we got more than 2,500 cases. This is the schedulability impact for the single core protocols. In the x-axis of the graphs, we have the utilization cap, and in the y-graphics, we have the schedulability ratio. You can see below each graph the parameters that we varied and we used. So in continuous lines, we can see the theoretical values for each of the protocol. And on dotted lines, we can see the theoretical values, but using our overhead on it. So we can see that the PCP, IPCP, and SRP degraded the most, and PIP stays quietly the same. This is the schedulability impact for the multi-core protocols. We can see in the x-axis the utilization cap, and again in the y graphic the schedulability ratio. In red and yellow continuous lines, we can see the theoretical values for the partitioned RM and EDF. In blue and green, we can see the continuous lines for the theoretical values of MSRP and MCP. We varied the number of resources between the graphics. Here we can see the MPCP stays quietly the same when we vary the number of resources, and the MSRP degrades the most when we vary the number of resources. After evaluation, we can see that a correct design and implementation allow a small memory footprint and runtime overhead. We can also see that our design has overall few impact on system schedulability, and we pretend to extend our experiments for nested locks. So thank you very much for your attention and for watching this presentation.